Welcome to this Explainer. Think of this as your ultimate high school chemistry study guide to mastering the evolution of atomic theory. We're going to trace a really fascinating chronological narrative today, starting from early philosophical musings and going all the way to the empirical discovery of neutrons. We'll explore exactly how experimental anomalies forced brilliant scientists to continuously rethink the physical world. If you want to understand not just what the atom looks like, but exactly how we figured it out, you're in the right place.
Okay, let's look at our agenda for today. We'll be covering 1. Philosophers to Dalton. 2. Cathode rays and electrons. 3. The plum pudding model. 4. Rutherford's gold foil experiment. And finally, 5. Protons, neutrons, and nuclei. Let's dive right in.
Philosophers to John Dalton. We're beginning our journey by looking at the macro-level philosophical origins before we zoom progressively deeper into the atom itself.
It's kind of wild to think about, but these early ideas remained completely dormant for a massive chunk of history. Around 400 BC, Indian and Greek philosophers proposed that matter had fundamental building blocks. But honestly, these were just philosophical speculations. They had absolutely no way to test them. It wasn't until 1808 that a British schoolteacher named John Dalton transformed this philosophical speculation into a formal scientific theory, proposing that the atom was the ultimate indivisible particle of matter.
So the crucial takeaway here is that both those ancient philosophers and John Dalton firmly believed you literally could not divide matter any further than this. I mean, the very word atom comes directly from the Greek word atomio, which literally translates to uncuttable or non-divisible. And Dalton's atomic theory was incredibly successful at the time. It perfectly explained the law of conservation of mass, the law of constant composition, and the law of multiple proportions. For a while, it seemed like we had the ultimate answer to the nature of matter.
But science is driven by anomalies, right? Dalton's theory explained a whole lot, but how on earth do we explain static electricity? By the end of the 19th century, it was well known that if you rub substances like glass or ebonite with silk or fur, they actually became electrically charged. This experimental failure, the fact that friction somehow created electrical charges, totally broke Dalton's uncuttable model. Because think about it, if atoms were just solid, uniform spheres, where was this electrical charge even coming from? This question forced a massive scientific breakthrough and really set the stage for modern empirical science.
Section 2. Cathode rays and electrons. To solve that static electricity mystery, scientists in the 1850s started experimenting with electrical discharge in partially evacuated glass tubes.
Early hints actually came from Michael Faraday's laws of electrolysis. But in the 1850s, scientists began using cathode ray discharge tubes. Now, what's really interesting here is how surprisingly simple this setup was. Literally just a glass tube, 2 thin metal electrodes, and some evacuated gas. When they applied a really high voltage across these electrodes, a stream of particles began moving from the negative electrode, the cathode, over to the positive electrode, the anode. By coating the tube behind the anode with phosphorescent zinc sulfide, scientists could actually see a bright spot develop the second these invisible rays struck it.
And this brilliantly illustrates how a 19th century scientific inquiry directly connects to modern technology. If you've ever seen one of those older, bulky TV sets, you were literally looking at a cathode ray tube. The pictures you saw were simply the result of these cathode rays causing fluorescence on a television screen that was coated with specific materials. It's a perfect example of how foundational physics directly enables the concepts driving our everyday tech.
Through rigorous testing, scientists figured out some really incredible characteristics about these rays. They travel in straight lines unless exposed to electrical or magnetic fields. When they were exposed to those fields, they behaved exactly like negatively charged particles. And here is the absolute most important part. The characteristics of these negative particles, which we now call electrons, did not depend on the material of the electrodes or the nature of the gas inside the tube. Because these traits never changed, regardless of the materials used, scientists concluded that these negative electrons are a basic universal constituent of all atoms. So the atom, as it turned out, was absolutely divisible after all.
Building on that huge breakthrough, we knew electrons existed, but we really needed to know their exact charge. Enter R.A. Millikan, who solved this with his famous oil drop experiment between 1906 and 1914. He basically used an atomizer to spray a mist of oil droplets into a chamber. He then passed a beam of X-rays through the chamber to ionize the air inside. Those oil droplets acquired an electrical charge by colliding with these gaseous ions. By observing the droplets fall and applying a carefully controlled electric field to counteract gravity, Millikan was able to calculate the basic electrical charge of the electron as -1.6 times 10 to the power of -19 coulombs. This was just a monumental achievement in experimental physics.
Section 3. The Plum Pudding Model. So, knowing that negative particles definitely existed, J.J. Thomson had to propose a brand new framework to explain the overall stability and neutrality of the atom.
Because atoms are electrically neutral overall, Thomson knew that if negative electrons existed, there just had to be an equal amount of positive charge somewhere. Here's a crucial point for your exam. Thomson's 1898 model, which is often compared to a watermelon or a raisin plum pudding, assumed the atom was a sphere where positive charge was uniformly spread out and the negative electrons were just embedded within it, kind of like seeds in a watermelon. The fundamental takeaway from this visual analogy is that the atom's mass was assumed to be completely evenly and uniformly distributed.
But science never just stands still. Meanwhile, pioneers like Henri Becquerel, along with Marie and Pierre Curie, were developing the whole new, fascinating field of radioactivity. They observed that certain elements emitted radiation entirely on their own. During this phase, they observed three distinct kinds of rays being emitted: negatively charged beta rays, neutral gamma rays, and high-energy, positively charged alpha rays. Rutherford eventually found that alpha particles carry 2 units of positive charge and are essentially helium nuclei. This new radiation provided a brand new, highly energetic tool to probe Thomson's plum pudding model.
Section 4. Rutherford's Gold Foil Experiment. Armed with these high-energy alpha particles from radioactive sources, Ernest Rutherford set out to officially test Thomson's uniform mass theory.
Rutherford devised this brilliantly simple yet completely profound setup. He directed a stream of high-energy alpha particles at an unimaginably thin piece of gold foil. We're talking just about 100 nanometers thick. He then surrounded this foil with the circular fluorescent zinc sulfide screen. The goal was pretty straightforward. Just watch where the tiny flashes of light occur to see exactly where the alpha particles end up after hitting the gold atoms. Because alpha particles are quite heavy and positively charged, Rutherford fully expected them to just blast straight through Thomson's uniform pudding of an atom with almost no deviation whatsoever.
Well, the results were completely unexpected. While most alpha particles did pass straight through just as predicted, a small fraction deflected at slight angles, and incredibly, a very few, about 1 in 20,000, bounced nearly 180 degrees right back toward the source. Rutherford was absolutely shocked. He later described it by saying it was literally as if you fired a massive 15-inch artillery shell at a piece of tissue paper and it came straight back and hit you. Clearly, Thomson's uniform mass model was fundamentally flawed.
This reveals a massive paradigm shift in how we view the physical world. Let's remember the absolute basic rule of charged particles. Like charges repel each other. Because those heavy positive alpha particles were violently repelled, the positive charge inside the atom simply couldn't be spread out evenly. There had to be a really dense, incredibly small, positively charged nucleus aggressively pushing those alpha particles back. Rutherford concluded that most of the atom is actually empty space, with the positive charge and almost all of the mass concentrated in a tiny central volume, which we now call the nucleus.
Section 5. Protons, neutrons, and nuclei. Rutherford's nuclear model beautifully set the stage for finding the actual heavy particles living inside that tiny, dense central volume.
Experiments with modified cathode ray tubes had actually already revealed canal rays carrying positively charged gaseous ions. By 1919, the smallest and lightest positive ion was isolated from hydrogen and officially named the proton. But the math was still a bit off. The mass didn't quite add up, leading scientists to suspect there was another particle hiding in there. Finally, in 1932, James Chadwick bombarded a thin sheet of beryllium with alpha particles and discovered electrically neutral particles with a mass slightly greater than a proton. He named them neutrons. Notice how our chronological journey is complete. We went all the way from ancient uncuttable spheres to discovering the electron, then uncovering the dense nucleus, defining the proton, and finally finding Chadwick's elusive neutron.
You might want to take a screenshot of the high-yield study table we've got here. Understanding these specific contrasts is absolutely essential for your chemistry exams. Notice how the electron and proton have the exact same magnitude of charge, roughly 1.6 times 10 to the 19 coulombs, but opposite signs, while the neutron just sits happily at 0. And look at the mass. Protons and neutrons are the heavyweights with a relative mass of 1, while the electron is so remarkably small it's effectively 0. This table perfectly summarizes the fundamental subatomic building blocks of our universe.
Which leaves us with a totally fascinating final thought.
We now know the atom isn't a solid sphere, but mostly empty space with a really dense core. But wait, opposite charges attract, right? So if the negative electrons are just zipping around a dense positive nucleus in all that empty space, why don't they just spiral inward and crash right into the center, destroying the atom entirely? Rutherford gave us the nucleus, sure, but classical physics completely failed to explain atom stability. It would take a whole new era of quantum models, wave functions, and quantum numbers to finally replace these mechanical views and explain the true, bizarre behavior of the physical world. But hey, that is a profound mystery for another explainer. Keep questioning, keep learning, and I'll see you next time.